But first, I need to get some definitions out of the way, and this is kind of some recall that we've talked about in Physics 101 and 102. First of all, atomic number, that's the element that we're looking at, and it's the number of protons that tell us what element we're looking at. Again, atomic number. The nucleus is where all the protons and neutrons are living at. It's the nucleus of the atom. Could even talk about how many nucleons there are. And lastly, the mass number of an atom is just going to be the number of protons plus the number of neutrons, because all of the mass of an atom comes from the protons and the neutrons. The electrons are not very massive. They're about 1,000 times less massive than the protons and the neutrons. Just a little bit of practice. I know you saw this in Physics 101, but it's worth stating again because it's kind of important when we talk about transmutation. Suppose we had carbon, and carbon has 6 protons. That's what tells us that it's carbon. And one isotope of carbon would have 6 neutrons. Atomic mass number is going to be 6 plus 6. Atomic mass number would be 12. We would write this as carbon 612 or carbon 126, and that tells us what isotope of carbon we're looking at. Another stable isotope of carbon has the 6 protons. It's the 6 protons that tells us that it's carbon. It also would have, this one would have 7 neutrons. That's what makes it an isotope. And take 6 plus 7, and we're going to find out atomic mass number is 13. We would write this as carbon 13-6. 6 is the number of protons. 13 is the atomic mass number. Now, before I get into the flavors of radioactivity, I need to kind of get in writing what we know that it is. And I've already mentioned this. If we have something that is unstable inside the atomic nucleus, it wants to lose that energy. It wants to drop to a lower energy state. We call this process just radioactive decay. And what's the atom, or what the nucleus is going to do, is it's going to try to emit some form of energy. That energy could be in the form of particles, like an alpha particle or a beta particle, or it could be in the form of an electromagnetic wave, like a gamma ray or even an X-ray. Essentially, what it boils down to is unstable nucleuses want to get rid of energy. They want to become more stable. Now, let me just talk about what holds atoms together, because that's going to be important to having a stable versus unstable atom. Suppose I had 2 positive charges. Well, we know that 2 positive charges want to repel each other. And that's because they have the same exact charge, and that's what the electrical repulsion would be. However, inside of a nucleus, we're going to have what's called a nucleon, which is going to be the protons plus the neutrons. And yes, 2 positively charged protons would repel each other. And this would be an example of helium. Remember, helium is going to have 2 protons and a certain number of neutrons. Let's just, for example, say that we're going to have 1 neutron, and what that neutron does is it acts like glue, and it has this thing called the strong force. The strong force is very, very, very strong, hence its name. It's one of the 4 fundamental forces in nature. We have gravitational, electric, the strong, and the weak nuclear forces. The strong force is attractive, the electrical force is repulsive. When atoms are close together, the strong force is very significant. The electrical force is also very strong, but is not as significant. So if they're really close together, the strong force wins. If atoms are far apart, the nuclear force drops off very rapidly. So if we take a look at this case right here, very insignificant, significant, the electrical force wins. This setup, these protons are more likely to fly apart than in this example right there. And that's kind of one of the things that makes nuclei unstable. Things that are small tend to be relatively stable. Here we have an example where the nucleons are close together. The nuclear strong force would win, and this guy would be relatively stable. This one has the nucleons far apart. This guy is far more likely to be unstable than it is to be stable. So the more stuff we have, the bigger it has to become, and the more unstable it tends to be. Something else we have to keep in mind is a neutron by itself won't live for very long. It's actually radioactive. It needs protons around it in order for it to survive. Now, what do we know about neutrons? Well, neutrons are going to have no charge and lots of mass. So what a neutron by itself is going to do is it's spontaneously going to be radioactive, and it's going to decay. It would decay into a proton and an electron. So here's my neutron, and it spits that guy out. So it's going to have a negative charge and a positive charge. Not a lot of mass and lots of mass. So it's neutral. Most of the mass goes here. Little teeny tiny bits goes there. Negative charge and positive charge. Again, a neutron needs protons around to keep this from happening. Now, with those two things in mind, we can talk about the nuclear stability belt. And what I mean by that is, suppose we were to take a look at the atomic number, and the atomic number would increase as we increase the number of protons. And as we did that, we're going to have to add on more neutrons in order to hold these protons together. That kind of makes sense. But as we do so, we're also making this element bigger. And as we make it bigger, it takes more protons per neutron in order for this to happen. So if we were to plot the number of neutrons on here, kind of a one-to-one line might do something like this, and we would actually call this like a stability line. The closer elements are to this line, the more likely they are to be stable. But as you can see, we need to pack more neutrons on here, and it tends to deviate further away from this stability line. It turns out that the magic number is about 92, and that's 92 protons, and this element is going to correspond to be uranium. We all know that uranium is kind of unstable. We call elements with a number greater than 92 transuranic, and these are elements that tend to be unstable. They're not very likely to occur in nature, and they're not likely to live very long. We can actually create elements up here. We can create them in the laboratory, but they're going to live for micro, nano, or picoseconds. Just taking a really quick look at the periodic table, we can kind of see if we work our way right here. There's the magic number, 92. Pretty much anything above this guy is going to be unstable. It's going to be radioactive. So uranium, unstable. Even things like thorium are kind of unstable. Plutonium, you've probably seen that in bombs and stuff like that. Anything above that line, that magic number 92, is going to be unstable. And we have actually created some elements out here. This table is slightly out to date, but these things don't live very long. So now that we know what radioactivity decay is, now let's talk about the forms of radiation that could be emitted by a radioactive sample. And bear in mind, it could emit one or all of these guys at the same time, kind of depending on what type of source we have. Let's, for example, say we have radium, and this radium is, of course, enclosed in a safe lead block because none of these guys can penetrate it. I'll talk about penetration in a little bit, but it could be spitting out any forms of radiation. It could be spitting out alpha radiation, and essentially an alpha particle is just a positively charged helium nuclei. It's going to have a +2 charge, and it's going to have 2 protons, and it's going to have 2 neutrons, and so it's actually going to take away an atomic mass of 4 from the element. It's also going to knock the element number down by 2. A beta particle is just an electron, essentially. Now, how this comes about, well, if you remember a couple of slides ago, we had a neutron, and that neutron spontaneously decayed into a proton and an electron. So when beta emission occurs, essentially a neutron turns into a proton. The mass number does not change. However, the atomic number, the element, does with beta emission. Gamma emission is the easiest. It's just electromagnetic radiation. If we were to put a magnet, say a north and a south right here, well, a beta particle is going to have a negative charge. It may bend this way. A alpha particle would have a positive 2 charge. It's going to bend that way, and gamma radiation would not be affected. Now, before I go into what happens and how these guys can change or transmute elements, I do want to talk about their relative strengths or their relative penetrations. Alpha particles are going to be the weakest ones of these guys, and these guys are going to not be able to penetrate paper. Alpha particles cannot penetrate our skin, our clothing, and stuff like that. However, if we were to ingest an alpha particle, that would probably be a bad thing because the radiation would not be able to get out of us. Beta particles are going to kind of be the midpoint. They can penetrate paper, but not aluminum. And last but not least are going to be gamma particles, and gamma particles are going to be the strong ones. These guys can penetrate paper, they can penetrate aluminum, but they can't really penetrate lead. It'll take some thickness of lead in order to stop the most energetic ones. So alpha is the weakest, gamma is the strongest. Now, this just kind of summarizes the three types of radioactive emissions that we have. And here we're looking at neutrons that are blue, and we're looking at protons that are red. And what we can kind of do is we can kind of say that here we have an element, and pay attention to the mass number. The mass number is 241. If this thing spits out an alpha particle because it's decaying, then it's going to lose 2 protons, those are the red ones, and 2 neutrons, those are the blue ones. So its mass number is going to go down by 4. It's losing 2 protons, so it also changes the element. Pretty important to know. For this guy right here, remember that this is a flavor of hydrogen. Hydrogen has 1 proton. And so what we can do is we can say this particular isotope has 2 neutrons associated with it. One of these neutrons, this one right here, is spontaneously going to decay. It's spontaneously going to decay into a proton. The element goes up by 1 because of this. It goes from hydrogen to helium. It loses an electron throughout this process, and here's the electron that's going to be the beta particle. This does actually also spit out something called an antineutrino, but that's a subatomic particle, and your book doesn't go into there, so we're not going to talk about it. The last form of radiation is going to be gamma radiation, and suppose we had some helium, and this helium is very excited. You see how far away these guys are? Well, it wants to shed that energy, and so it spits off a gamma particle. It spits off a photon, and they all become closer. Doesn't change the element, doesn't change the mass, doesn't do anything like that. Now, I went ahead and put together this nice little cheat sheet of the kinds of radioactivity and what's going to happen. Let's talk really quickly. Alpha decay spits off a helium nuclei. It's going to decrease the mass number by 4 and decrease the atomic number by 2. Beta is going to spit off a beta particle. Not going to change the mass. A neutron changed to a proton. But it is going to change the atomic number because we gain a proton. Gamma emission, that's the easiest one. It's just going to emit some energy, not going to change either one of these two. Now we're kind of back to some of the books pictures here. It's essentially what I've shown you already, alpha emission and beta emission. Suppose we had something and it was unstable, then a neutron is going to become far enough away from the protons that it's going to spontaneously form a proton and an electron. So we form a new proton, that's that guy right there. We form an electron and a beta particle is emitted. Now this element could still be unstable, and maybe it's unstable such that this little chunk right over here flies off. This one would emit the alpha particle. Bear in mind again that we're going to increase the element by 1, we're going to decrease the element by 2. Mass number stays the same, mass number decreases by 4. Now, kind of what goes on when we gain or lose protons is we're changing the element, and the fancy word for that is we're transmuting the element. In alchemy, they were trying to transmute lead into gold, and it turns out you can actually do that process, but it's more expensive than the gold itself. But that's a different topic. Let's just talk about alpha and beta emissions for a second. Let's consider something like uranium. Uranium is going to emit many things, but let's just suppose for a second that it emits a alpha particle. Here we have uranium, and we have the mass number on top. We have the number of protons right down here. If it emits an alpha particle, it's going to drop the mass number by 4. It's going to drop the number of protons by 2. What's going to happen is it's going to drop this guy right down here from 92 down to 90. This guy's going to drop by 4. You drop it from uranium, it's going to turn into thorium. Bear in mind that this number right here is a conserved quantity. 234 plus 4 should be 238. And this number down here, 92, should be the sum of these two. So we're not creating protons, we're not destroying neutrons, we're kind of not creating or destroying mass is what we're saying. If we were to go ahead and take a look at the atomic table, or the periodic table, that tells us what we're transmuting to or from. So here we have uranium. We know we're going to drop by 2, so we're going to drop into thorium. Now, it turns out that thorium is a natural beta emitter. So let's consider the beta emission from thorium. Here we have thorium-234. 90 tells us that it's thorium. If this guy were to emit a beta particle, what's going to happen is one of these neutrons is going to turn into a proton. So there's the neutrons dropping, there's the protons increasing, and that is also going to change the atomic number. This is going to increase by 1, and that changes it into this element right here. Bear in mind that this number does not change, and the same thing kind of holds. What we can do is we can say that this electron is going to come spitting out. The 0 just kind of says that there's not really much mass going on with this, and the -1 is just kind of the charge of the electron. I personally prefer to put it up here, but each to their own. If we were to come back to this guy right here, now we're talking about the beta emission. It's going to increase the element by 1, so we're going to go from 90 up to 91. So the periodic table will come in useful for these problems and for your homework. Now just a really quick show of a simulation here. This simulation is going to be of alpha decay, and we're going to have neutrons, protons, and alpha particles. And I'm just going to reset all of my nuclei. It's kind of a lead-in to when the decay is going to kind of happen-ish. But we're going to start off with polonium, and we're going to end up with lead. And I'm just going to reset all the nuclei. They're shaking because they're unstable, and as you can see, they're firing off alpha particles. Now, I put 10 on here, and it turns out they're all not going to fire off at the same exact time. Some of them are still kind of active. They're going to decay, not quite randomly, but they're going to have some half-life where roughly half of them have done their decaying. And that's kind of important in the next couple of slides. Quick little look at beta decay. What we can do is I can add 10 atoms from a bucket of atoms, and we have neutrons, protons, electrons, and then this little subatomic particle called an antineutrino, and the same thing kind of happens. These guys are excited, they're shaking. A neutron changes into a proton, and it spits off the electron and technically the antineutrino. And again, there's some time that it takes for this to happen, and not all of them happen at quite the same time. Now, really quickly, I want to talk about what happens as radioactive decay or radioactive emissions interact with our body. Bearing in mind that alpha particles are the weak ones, beta particles are in the middle, and gamma particles are the most powerful. Now, all of these particles, or waves if you will, doesn't really make a difference, does it? Can add energy to the body's tissues. And what it can do is it can actually break apart our DNA, and that's probably not a good thing. Now, alpha particles can't really penetrate skin or clothing or stuff like that, but if it gets inside of us, then that could kind of be a bad thing. Now, I do want to kind of dispel the myth that all radiation is bad, and perhaps more so, that if something has been irradiated, that it's all of a sudden radioactive and glowing green and stuff like that. We can irradiate food, and we can do that to kill microbes. For example, here we have some strawberries, and they've been irradiated by some form or another, and that kills the microbes, and it's less likely that stuff's going to grow on them. It does not make the food radioactive, so the stuff is not glowing green after that happens. Astronauts in space, their food is first irradiated because, well, diarrhea in space would be a very bad thing, but the astronauts are not radioactive. In many cases, radioactivity is a good thing in the health professions. We can use things like radiotherapy to treat things that could otherwise go untreated. Suppose, for example, that someone had a tumor or something deep inside of their brain, and obviously we can't cut into the brain. We know that that's a bad thing. However, if we were to have a source, and it could be a gamma emitter, contain that source in lots and lots and lots of lead, because you don't want it spitting everywhere. But if we were to have a slit, and we could use that slit to focus these gamma rays. Remember, gamma rays can be constructively interfered or destructively interfered, so they focus just on the parts that we want to try to, let's see, what's the right word? I don't want to say cut, but we want to get rid of. We can use the wave-like nature of gamma rays in order to accomplish things that could not be done otherwise.